All right, a quick review of what we talked about last class. We were talking about some more linear independence results. So if you remember from last class, the idea was if we had a linearly independent set and we had a vector that wasn't in the span of that linearly independent set, we could put that vector u in there and get another larger linearly independent set. So we can enlarge linearly independent sets by just putting in some vectors that aren't in the span of your set. And we can do that over and over again. So we proved that last day. And just as a reminder here, we said that the dimension of a vector space was just the size of any basis. Remember, a basis we're thinking of as a linearly independent spanning set of a vector space. And using the idea on the last slide, if we have a finite dimensional vector space with some linearly independent subset, we can always enlarge that subset to become a basis. And so basically we just do theorem 5.1 over and over again. We take our linearly independent set, we find something that's not in the span, call it u1 in this case, and we add that to that linearly independent set I, and now we have I1. So it's the original set plus that original vector. We check if it spans, and we keep going. If it doesn't, we would make I2 by picking another vector not in the span of I1 and adding it. So that's how that works. And if you remember, well, we know the dimension is finite, and we're increasing the number of linearly independent vectors in our set I here every time. So eventually it'll have to be the dimension of our vector space by definition. It'll be a linearly independent spanning set. And that's where we ended off. So I want to keep going and talk about a couple of other results here. So suppose we do indeed have a spanning set of a vector space V. So let's say it has m vectors, not necessarily linearly independent, but we just know that we can make all of V by linear combinations of these guys. Maybe there's some redundant vectors in there, but we know that the span of all of these guys is indeed this vector space. Well, the first result here says that, well, there has to be a finite basis, let's call it B, and the size of that basis is at most m, the number of vectors in our spanning set. So we can't have a basis with more than that. The second thing, and this is across 2 slides, so we'll talk about it here on the next slide. And it says that, the second part, if we have a linearly independent set, we can enlarge it to a basis by adding vectors from any fixed basis of our vector space V. That's very, very important, very, very interesting. And the third thing says that if we have some subspace, sorry, this B got erased somehow, subspace of V, then we know the dimension of that subspace has to indeed be finite, of course. And if we have a basis of U of the subspace, we can enlarge it to a basis of the vector space itself. So let's just talk about why these are true. I'm not going to prove these in precision, but I'll give you a hand-wavy proof of this. Okay. So for the first thing, saying that the dimension of V has to be at most m, well, start with V1 in our set and just apply that lemma 5.2 over and over again. Just keep adding vectors to your set until you have a basis. The second part here says that if we do have some sort of basis of V, let's say that there are n vectors in them, e1 up to en, there's our basis, and we have some linearly independent set, I, of vectors, well, we can check if that's already a basis. So if it spans V, it's a linearly independent set that spans V, it's already a basis, and we're just done. We're trivially done, we didn't have to do anything. But maybe it doesn't span. So what we can do is the following. We can note first that, of course, B isn't in the span of I because B is a basis, and we're saying that I isn't a basis, so there's no way that the span of I includes all of B, otherwise it would be a basis. So since that's the case, we know there's at least one element of our basis. I'm using BI, should really be EI. Let me change that so these should be E's, not B's. So let me change these to E's. So there has to be one basis vector that's not in the span, right? Because this isn't a subset of the span. There has to be one thing that's not in it. So we can use lemma 5.2 again. We can just take that vector, EI, whatever it was, and add it to our original set I, and check, is that now a basis? If not, we just do that process over and over again. And the third result, I'm just going to leave for you guys to read here. So you'll find that on page 370. It's not particularly hard, so have a look at that on your own time. Now let's look at a little bit of an aside where we can talk about vectors in, we can think of it as Rn, but we can do this over any field, so we'll call it Fn. And we'll talk about how we can use the idea of matrices to help us determine if a set of vectors is indeed a basis. So I'm not going to prove this. I'm going to leave this as something for you guys to look up. But it's a very useful result when you're dealing with your usual vector spaces like you dealt with in linear algebra 1. But again, we don't have to do it over the field of real numbers. We can do it over any field we like. We can just have column vectors, right? So if we were in, say, F3, F is any field you like, and then vectors in that are going to look like A, B, C, where A, B, and C are just elements of whatever field you happen to be in. Maybe it's the real numbers. Maybe it's one of those finite fields like Z5 or Z11, something like that. Or maybe it's the complex numbers or any other field. So this result says that there's 5 things that are equivalent. And it has to do with matrices. The whole idea is if you take n vectors from Fn and you glom them together in a matrix, you can check if those n vectors are indeed a basis. And we'll show in a little while that we only need one of these to be true if we have n vectors. So this bit is nice and easy, which we'll see in a result going forward. Again, I'm not going to prove this, but the whole idea is that if the matrix that you get by glomming those n vectors together is an invertible matrix, then those n vectors are indeed a basis. And you can either glom them together in columns, or you can glom them together in rows. So I'll write basis here for both of these. So those vectors, you glom together. You can glom together as columns, or you can glom them together as rows, and all you need to do is check if that matrix is invertible, and indeed you are good to go. You have a basis. And you could think that, well, this is only applicable to Fn, right? When you have kind of n-dimensional column vectors. But as we'll see later in the course, this result here is going to be incredibly useful. Because for finite dimensional vector spaces, in some sense, if you can deal with Fn, you can deal with any finite dimensional vector space. This is kind of all we have to worry about. But there's a little bit of work to get there. And to see why this is true, the proof is on page 287 of your textbook. I will say that it only does the case when the field is indeed the real numbers, but this can apply and the proof can just go forward exactly by replacing R with any field that you like. So let's continue now and see how this works. So let's say let's be in R5 here. So let's say these guys here are all in R5. So we'll deal with the field of real numbers. But again, as long as it's a field, you can still do linear algebra. So first of all, I want to note that indeed these are linearly independent vectors, and it's pretty easy to check. So it's pretty easy to see here that indeed these are linearly independent vectors. Imagine that I wanted to take linear combinations of these three guys to make the zero vector, so all zeros. Well, first of all, since these guys are both zero in the first entry, that tells you that the coefficient for this guy has to be zero. So I know I need a zero here. And then similarly, since both of these guys have a zero entry in the second, well, really we only needed to check this one because this guy's already zero. So that tells me that this has to be zero. And then finally, well, we need zeros here. And the only place that is non-zero right now is this second vector. So that coefficient would have to be zero. So these three guys, just by inspection in some sense, are linearly independent. Okay. So my thought is as follows. So I want to make this a linearly independent set with two more vectors. And the whole idea is I'm going to try and come up with a matrix. I'll just do this by columns. You could do it by rows if you like. It doesn't matter. So I need two more columns so that this matrix is invertible. So it does not have a determinant of 0. Remember that A inverse exists if and only if the determinant of A isn't 0. So thinking about this in terms of linear independence, I'm thinking that, well, this column vector here, this is the only way out of the three where I can determine what the first entry of a linear combination would be, since it's the only vector that has something non-zero there. So I'm going to think about this guy as the vector that determines the first entry in some sense. And similarly, I'm going to think of this guy as being the vector that determines the second entry, since this one is the only one that's non-zero. So I have a way of getting the first entry and the second entry. Now, if I wanted to make a spanning set, so I wanted to have a linear combination of vectors that could make any vector in R5 here. I need to come up with a way of determining the third, fourth, and fifth entry. And I'm going to say that this guy will determine the third entry in some sense. So I'm going to let this guy determine the third entry, and then I can make up for these entries here with the two vectors here. So if this is determining the first, the second, and the third, well, the fourth entry we can say will be determined by that guy, and the fifth entry will be determined by that guy. And they're not the only choices. That was just my thought process for coming up with two other vectors. And indeed, we could use the fact that we know, in fact, this is the standard basis, and we'll talk about standard bases in a little more detail in a little bit, but a standard basis for R5 is called the standard basis. So it's just exactly what you expect. So it's a 1 in the first entry and zeros in the others, and then a 1 in the second entry of your vector and zeros in all the others, and then your third entry, your fourth entry, and indeed your fifth entry. That's kind of the most natural basis. If you want to make any vector in R5, it's pretty easy to do with these, taking a linear combination, and clearly these are linearly independent, so it's a linearly independent spanning set. So obviously it's a basis for R5. And we could say, since this is a basis and we have three linearly independent vectors, we can use the previous theorem to enlarge this set by adding some vectors from another basis, like the standard basis. And in fact, these two would do. I'll add this guy and this guy. And then we just need to check, let me call this matrix here A, and I'll leave this as a little exercise. It should be fairly easy. Just check that the determinant of A is something that's not 0. As soon as you know that you have indeed a basis. It's these three vectors plus these two. Or, equivalently, remember, the columns are a basis if and only if the rows are a basis as well. So you have another basis here as well. So these 5 vectors, if you look at them as column vectors instead of row vectors, are another basis for R5. So that's how useful the above theorem is. It allows us to use our linear algebra 1 techniques to talk about bases and linear independence. Let's do this example here. Let's get back to the complex numbers as a vector space. And just as a side note, before we start this, a side note, the standard basis for the complex numbers is usually the set, in fact is always the set, just 1 and I. So you can make every complex number a plus bi by taking a copies of 1 plus b copies of I. So that's the standard basis for the complex numbers. But what we want to show is that if we have some complex number that's fully complex in the way that it has both a real part and an imaginary part, so neither a nor b is 0, we want to show that the set z along with the conjugate, and I'll just remind you what the conjugate is. So the conjugate is a minus bi, so remember the conjugate just means to swap the sign between the real and the imaginary part, that is indeed a basis. So remember, for something to be a basis, it needs to be a linearly independent spanning set. And we could use some theorems to do this a little more easily. But let's do this from first principle. So let's show that this indeed is both linearly independent and a spanning set. So I'm going to call this S, just to make a name for it. Okay, so let's show, first of all, that S is linearly independent. So we need coefficients, let's call them R and S, in the real numbers. Remember, the set of scalars for the vector space of the complex numbers are real numbers. And we want these coefficients to be such that R times Z, and Z is just A plus BI, plus S times the conjugate of Z, so A minus BI, that equals 0, or 0 plus 0i. And we can indeed expand this out, and I'll leave this as just a little calculation for you guys to do. But if you do so, you'll see that you get A times R plus S must equal 0. And again, maybe we should view this as 0 plus 0i. So if we equate the real parts, we get A times R plus S equals 0. And if we equate the imaginary parts, we get that B times R minus S has to equal 0 as well. Now remember that we picked our complex number Z such that A and B were not 0. And we have two numbers multiplied to give us 0. So we know that since A isn't 0, we know that R plus S must be 0, or R has to equal minus S. And similarly, since B isn't 0, we know that R has to equal S. R minus S has to be 0. And the only numbers where R equals S and R equals minus S, of course, is 0. So R and S both equal 0. So we proved indeed that S is linearly independent. So that is great. Let's prove that it's indeed a spanning set now. Remember, we could use a result to just say that this is enough. And in fact, after this, we'll see a very powerful theorem that says if we know something about the size of a basis, and if we have a linearly independent set of that size, it must span. But just for practice, let's show that it also spans. So let's show that S, or let's say the span of S. So the span of S is indeed all of the complex numbers. So I need to show that some linear combination, A plus BI and A minus BI, so some linear combination of those two vectors, can give me any complex number I like. So let's let R and S again be scalars, and again, those scalars are going to be real numbers, such that R times our first vector A plus BI plus S times our second vector A minus BI. Remember, this is Z, this is Z conjugate. So that equals any complex number. So let's say C plus DI. And again, we can play a very similar game to what we did in the earlier part. We can equate the real and imaginary parts of these. And if we do so, again, I'll leave this as a little exercise. If we equate the real parts, we get, just like above, A times R plus S equals C. And in fact, I'm going to rewrite this because I want to use some linear algebra techniques. I'm going to rewrite this as AR plus AS equals C. And for the second one, I get B times R minus S equals D. And I'm going to rewrite that as BR minus BS equals D. Now, remember, R and S are our unknowns. So we're going to treat those guys as our variables. And if we think about this, we just translated this into solving a system of equations over the real numbers. We know exactly how to do this. So let's go ahead. We can put this into a matrix. So we want to solve the system of equations that looks like A, B, minus B, and then a dashed line, C, D. And indeed, there's lots of ways of solving this. You could just do this by row reduction, or you could do it by the inverse method. So we could look at this as the matrix. Let's call it big A, so that's going to be all of that stuff, times the vector RS, our unknowns, equals C, D. So we can multiply both sides by A inverse. Equals A inverse CD. And, well, A inverse and A cancel out to the identity, and the identity times RS is just RS. And indeed, RS is going to be A inverse times CD. So if we can figure out what A inverse is, we can multiply it by CD. So let's go ahead and do that. If you remember from linear algebra 1, we know that A inverse is going to be 1 over the determinant of A times the matrix where we flip where the entries on the diagonals are, so that's going to be negative B and A, and we negate the entries on the off diagonal, so that's going to be negative A, negative B. Great. So we need to determine what the determinant of A is. That's just AD minus BC. So it's going to be A times minus B minus A times B. So that's going to be negative 2AB. So this is minus 2AB times negative B, negative A, negative B, A. And I'm going to multiply that negative through just to make my life a little bit easier. So this is the same thing as 1 over 2AB. And I'm just going to change the signs of everything inside. B, A, B, minus A. Great. And now I'll multiply this through by 2AB. Remember, these guys are just real numbers, so that's no problem. So I'm going to multiply each entry by 1 over 2AB. And so in the first column here, let me actually do this here. Then the B's are going to cancel. I'm just going to be left with 1 over 2A. So let's go ahead and do that. So that's 1 over 2A, 1 over 2A. And similarly in the second column, it's going to be 1 over 2B, since the A's are going to cancel. 1 over 2B and negative 1 over 2B. So now I just need to multiply A inverse times CD. So A inverse times the column vector CD is going to be 1 over 2A, 1 over 2A, 1 over 2B, negative 1 over 2B times CD. And if we do that, we indeed get c over 2a plus d over 2b. That's your first entry. And the second entry is c over 2a minus d over 2b. So we can say, indeed, let me scroll up. We can say that R is c over 2a, c over 2a plus d over 2b, and S is c over 2a minus d over 2b. So that's great. And while this is a little bit of work, it does give us a formula for finding a linear combination of z and the conjugate of z for any complex number that you like. So let's just do a quick example of that here. So let's let z be what? Let's say 2 plus 3i. And we can say, if we wanted to make the vector 1 plus I out of this here, both c and d would be 1. So we'd get that we'd have our coefficient for z would be 1 over 2 times 2. So it would be a quarter plus d again is 1, and here b is 3, so this is 2 times 3 is a sixth, so this is a quarter plus a sixth. That's our coefficient for that, so that's a quarter plus a sixth of z plus, and similarly the sign just changes, so it's going to be a quarter minus a sixth times the conjugate of z. Remember, that's just 2 minus 3i. Conjugate just changes the sign. That equals 1 plus I. So if you like, we can simplify this. This is 5/12 times 2 plus 3i plus, well, a quarter minus a sixth. So that's what's that going to be? That's like 3/12 minus 2/12, so that's 1/12 times 2 minus 3i. That equals 1 plus I. And you can check that calculation to make sure that it works. But you can see how this idea not only shows us that it spans, but it gives us a recipe to come up with the coefficients for a linear combination of z and the conjugate of z for any complex number that we like. Now this theorem here is a really nice theorem in the way that it allows us to save some work as long as we know the dimension of our vector space. So if we do indeed know the dimension, so the number of vectors in a basis, if we have a set that's the same number of vectors as the dimension, so the same number of vectors as any basis, we only need to check one of linear independence and spanning. So if we have n vectors of a dimension n vector space, the set is linearly independent if and only if it also spans. So we know if it's linearly independent, it also spans, and the reverse, if it spans, we know it's linearly independent. So let's show this. I'm going to be kind of a little bit quick about this, but the whole idea, if we have a linearly independent set, if we want to show that it spans, well, we know by lemma 5.2, we could enlarge S to be a basis by including vectors not in the span. But we know that indeed the size of any basis is n by definition, of what a dimension is, so we know that S is already a basis. And we know bases span already. We know that they're spanning sets. And similarly, let's say that we knew that S spanned and we wanted to show that it was linearly independent. Well, as a little exercise, which isn't too difficult, I'll leave this to you guys, but if we have a spanning set, it must be the fact that a subset of that spanning set is a basis. Kind of the hand-wavy version of it, we can throw away all the superfluous vectors, the ones that we can make with linear combinations of the others. But we know that a basis has indeed n elements, so the only subset of an n-element set that also has n elements is itself. So we know that the original set S must be a basis. So that's great. That says that if we ever have the number of vectors, that's the dimension, we only need to check one of linear independence or spanning to determine whether it's a basis or not. We have one, we get the other for free. And finally, let's do a little example here. So let's say we indeed have a matrix A, and it's a 2 by 2 matrix, and let's say it's over some field. The field doesn't matter. So our coefficients and the entries of our matrix exist in some field. So I want to show the following things, and linear algebra helps us to do this, that this equation here, A1 times our matrix A plus A2 times A squared plus A3 times A cubed plus A4 times A to the fourth plus A5 times A to the 5 equals 0. I can always find coefficients A1 to A5 that allow this to happen. So that's pretty cool. And it's not clear unless you're thinking about this in terms of linear algebra. Well, if we think about this, well, we know that the dimension of 2 by 2 matrices is 4. Indeed, we have a standard basis for this. And the standard basis is indeed, well, it's going to be a 1 in the first entry and zeros everywhere else, a 1 in the second entry and zeros everywhere else. I might as well write them all down. And so every possible combination of a 1 in an entry and a 0 in the other entries, that's our standard basis. Kind of the one that you would expect, the easiest one to deal with. So we know that indeed the dimension of 2 by 2 matrices is 4. So this set of A squared, all the way to A to the 5th cannot be linearly independent. Well, first of all, we know that the dimension of the vector space is 4, so there's no way that a set of 5 vectors is linearly independent. So that's by theorem 4.2. So we already know that. So that tells us by the definition of linear dependence that there has to be a set of coefficients which all aren't to 0, at least one of them is non-zero, where a linear combination using those coefficients gives us 0. So there must be, and I'll write this here, there must be coefficients, at least 1 not equal to 0, that satisfy the equation above. So that's pretty great. Thinking in terms of linear algebra, we don't have to get into the weeds of what these matrices are as powers. We just know that there has to be some scalars here that make this equal to 0.